Good evening, everyone. I am Sam here. My screen. Someone confirm in the chat if the screen. Okay. So the topic for today is graphs, and a graph is composed of set of vertices, set of edges, that is a relation between vertices. It shows the connectivity. There is an edge between these two vertices. You can think of 2 points. And graphs, one is an ordered graph and an unordered graph. In an ordered graph, there's an edge only in one direction, either A to C or C to A. So if you want to go to C and C to A using a single edge, you need to have two edges over here. And both are an edge from C to A. And an application in various domains, electronic circuits and networks, transport, present the load of a place using. You can, modeling any sorts of relationships. Let's say on the list, it is as a graph. Any two people who have a friend have a graph. Graphs are used for this. Graph terminology. Two vertices are considered adjacent if they have an edge, and degree of a vertex is defined as number of vertices. Consider this vertex. This has 1, 2, 3, 3 edges and vertices. So its degree is 3. Consider this 1, 2, 3. Also has a degree. Consider this 2. This is 1, 2. This has a degree of 2. And a path is V1, V2, V such that consecutive vertices are adjacent. So to here, okay, like this, 3, 2, 3, 3, 3, 3, or 3, 3, 3, 3, 3, 3. All are valid paths. Simple path is one in which there are repeated vertices. So if you consider this one, A, B, E, D, C, this is a simple path. And similarly, B, E, D, C is also a simple path. But if I do A, C, D, E, C, it will not be a simple path because we have a cycle, but after a simple path, the last vertex, add a vertex which is the starting vertex. A, C, D, and then the vertex A to the path. Again, it becomes a cycle. graph is connected if any two vertices inside it are connected by some path. There exists any path between those two, and the graph is considered connected. Here, for any two vertices, there is one path, but for consider this vertex and this vertex, no path. Subgraph is a set of vertices and edges. You know, vertices and edges form a set, like a subset of vertices and a set of edges, on, only having those vertices that are present in the subset. They create a graph. And then we have the notion of connected components. Now, consider this graph. You can consider this was you reach these three vertices, this vertex, and you cannot any other vertex in this graph. So we call this a connected component. Similarly, connected component. This is another connected component. Each connected component is a subgraph. These three vertices of the graph, these three edges are a subset of the graph. And we have a tree and a forest that is defined in the graph. A tree has no cycle. So the entire graph is formed without having any cycle in it. And forest is a group of trees. So each individual component is a tree in this example, and the entire graph. Now, how do we represent a graph when we are coding it? So we can store the vertices and edges in two data structures, and we can kind of store a reference from the edges to the vertices to the edges, so that we know which corresponds to which vertex. Voice break. Okay, a minute, I'll switch. Hello, is it better now? Hello, is is it better now? Anyone? Okay, let me continue then. Now, there is one representation is using an edge list. So in the case of an edge list, we store a container, an array, or a list technically, which has each node in the list contains a reference to the vertex in the graph. So consider this edge NW35. This has an this has an edge from BOS to JFK, and the next element in the list is DL247. This has an edge from Boston to John F. Kennedy to MIA, and A49. This has an edge from DFW to LAX, and so on. So now, if you want to find all the edges that are present, that are incident on a given vertex, you need to find which all are the adjacent vertices of a given vertex, or you just need to know the edges. You will have to traverse through this entire list, and that can be inefficient if you have to do that for each vertex. So this isn't a very useful representation in most cases. We have another representation which is called the adjacency list, and this is the most commonly used one. In this, what we do is we have a list for each vertex that stores all the vertices that are adjacent to it. So consider this vertex A. Adjacent to it are B, C, and D. This is stored as a list. For B, we have A and E as adjacent vertices. And this representation, using this representation, we can find the edges that are incident on each vertex in order of degree time, because there will be degree number of vertices and we just need to traverse this list. We already know which vertex it is, and the total space this occupies is, for each vertex we have 5 vertices, and now we have to add the degree of each vertex, because for each node we have degree number of elements in the list. So n plus degree of v, and the degree of each vertex, the sum of degree of all vertices is 2 times the total number of edges in the graph. And we can even prove this very easily. Consider any edge. This edge, while adding the degree of the vertex, this edge will appear in the summation twice. Once consider this edge AC. This will come appear in the summation for edge A, for vertex A, and for vertex C. So every edge appears twice. So this will be 2 times sum of degree of V, which is 2 times m, and in the order notation we can remove the constant. So it will be order of n plus m. And there is another representation which is adjacency matrix. This is a matrix of n cross n, where each entry in the matrix is true if there is an edge and it is false if there is no edge. We won't be using this representation for the algorithms we'll discuss today, but for a few algorithms this representation is very useful, especially for finding distances between each pair of the vertices. And so now once you have the graph, you might need to extract information from it. Let's say you have to find what are the connected components. We just need to find how far each vertex is from the current vertex. So for all this we need some systematic algorithms that we can use to search the entire graph, and they need to be efficient. You can't, because graphs are usually very huge. You have millions of vertices in a practical graph. So even having a complexity of n square will considerably slow down your code. So the first algorithm we'll discuss is breadth first search. A breadth first search traverses a connected component of a graph, and it defines a spanning tree. Now we haven't defined what a spanning tree is. Spanning tree, given a graph, a spanning tree is a subgraph of the original graph, which is a tree, and it spans the entire graph. So what does it mean by saying it spans the entire graph? Each vertex appears in the tree. Each vertex of the original graph appears in the graph of this. We have along each edge, and the distance that you reach, you assign them a distance of 1. Now what you do next is you suppose what is Hello. Sorry for the disconnection. Okay. So okay. So here you assign a distance of 0 to n. I add this s to my data structure called q, and it is a q data structure. What I do next is I look at the neighbors of s, which are r and w, assign them a distance of 1, and add them to q. After this, I what I do next is I remove w from q, and then I assign a distance of 2 to those neighbors of w which are not visited, that is t and x. And then what I do next is I remove r from the queue, and then I add a distance of 2 to the vertex v. Next, I remove t from the queue, then I add a distance of 3 to u because x is already visited. I don't update the distance to x. Next, I remove x from the queue, and then I update the distance of y to 3. Next comes v, no change happens here. Next I remove u, no change happens. And next I remove y, and we have the final distances for each vertex. The algorithm that the algorithm that we can write in code is this way. If you notice, the color of each vertex was white, and while it was in the queue, it was colored gray, and once it had been removed from the queue, it has been colored black. So we will use this to keep a track of where each vertex is. So for each vertex u in the vertex set, except for the starting vertex, we set the color to white, distance to infinity, and there is this pi array that will look at what it does. It is basically from which vertex updated the distance for u. So pi of u is nil because no vertex has currently updated the distance for u. And now we begin our algorithm with S. So color of S is gray, distance of S is 0, pi of S, this should be S. Pi of S is nil because no vertex actually updated the distance for S. And we add S to the queue. So while queue is not empty, we take the head of the queue, that is U, and for each V in the adjacency of U, now you can see why using adjacency list was a useful representation. Now if color of V is white, then we set the color of V to gray. We update the distance of V as distance of U plus 1. And now U is the vertex that is assigning the distance to V. So we set pi of V as U and we add in Q V to Q. And once we are done with all updations, we can dequeue the queue and set the color of U to blank. Now we can see that this algorithm, it updates the distances for all vertices and we also compute a pi array. What will be the running time of this algorithm? We enqueue a vertex only if it is colored white, and enqueuing and dequeuing takes over time. This was discussed in a previous lecture, and therefore also once the vertex is colored gray or black, it is never colored white again. So this step, that this enqueue step, will take a total of O of V time. Additionally, this all these other steps will also take O of V time each. Next, we only scan the adjacency list when the vertex is dequeued, and each vertex is dequeued exactly once. So we spend order of degree time on each vertex, and we do this for all vertices that are entered into the queue. So it will be O of V plus O of sigma of degree, which is the same as the cost we have for the adjacency list, space complexity. So sum of degree is O of E. E is for edges, V is for vertices. So the total running time is O of V plus E. And this is linear in the size of the adjacency list. And therefore this algorithm is pretty efficient. Now a few properties of BFS is, if I give you a graph and I give you a source vertex, all those vertices that are reachable from S will be discovered by BFS, because if you notice, you move along the adjacency list and you keep on spreading around the vertices. So any vertex that is reachable from S, at some point of the algorithm you will definitely discover that vertex. And it also computes the shortest distance to all reachable vertices. And this is somewhat difficult to prove intuitively, but the idea is that if you consider the distance that is updated here, if there was a shorter distance, you would have already updated it, because let's say the distance to V is 10 and distance to U will be 9 then. So if you say that the shortest distance to V is in fact not 10 but 7, then this step should have happened for some U which has a distance of 6. So you can move along this intuition to prove it formally. And now it computes a breadth first tree. If you look at this example, the tree is S to W, S to R, W to T. All these white edges are a part of the tree. You can look at the fact that it is acyclic. There is no cycle in this. And if you remember, we had computed a pi array, and this is useful to actually construct the tree, because each edge is from x to pi of x, because pi of w will be pi of x will be w. So there is an edge from x to pi of x, that is w. And for any vertex v reachable from S, the path in the breadth first tree from S to V corresponds to a shortest path in the graph. So whatever path that we find in the tree, any path in the tree is unique. Because there are no cycles, you can argue that every path in the tree is unique. And this path is exactly the shortest path in the graph. Also, predecessor subgraph of G. This predecessor subgraph of G is basically the breadth first tree. This is what I explained. There is an edge from pi of A to V. And G pi is the breadth first tree. V pi is all the vertices that are reachable from S. For all vertices in V pi, there is a unique simple path because it is a tree, and that is also the shortest path in G. And these edges in G pi are called tree edges. So another thing that to observe is that whenever is if the graph is connected, completely connected, this breadth first tree becomes a spanning tree for the graph because every vertex is reachable, therefore every vertex is present in the tree. Now I would call upon Nishan to show using BFS for solving a problem.
Uh, just a minute. I hope my screen is visible. I think it's visible now. So, hi everyone. I'll be discussing a problem on breadth first search, which is two buttons on code forces. So, basically, the problem statement is that we are given two numbers n and m, and and we can perform two operations in each turn, and the two operations are we can either multiply the number by 2 in each turn, or we can subtract 1 from the number n, and we have to find the minimum number of steps we have to do to make the number n equal to m. Okay, so I think, yeah. So how do we approach the problem using breadth first search? We can just make a graph which has this root node n, not a root node, just node n, and in each step we'll see that when we go left, we decrease the number by 1, or we can go right, where we multiply the number by 2, and doing the operations we reach number m here, and also another sequences of operations leads us to the number m here. So how do we find the how do we find the minimum length, minimum number of operations? So this is equal to the minimum length from the node n to the occurrences of the node containing the value m. So as you can see here, we have a length 2, which means that we have taken two steps, and while here we have 1, 2, and 3. We have length 3 from n to m, which means that we have taken 3 steps to reach from n to m via this path. So now to find the minimum, have we have to do a breadth first search. Why? Because search on the level wise, then we can see where we get the first occurrence of m. Okay, I hope this approach is clear. Why we're doing a breadth first search. And okay, so what the strategy will be is, as we just saw here before, we make a queue. First we push the value n into the queue, then we push the children of the first value in the queue, here it happens to be n, so we push the children n minus 1 and 2n, and we remove this because we have pushed this children. Now we go to the second value, which is n minus 1, and we push the value, suppose it's a1. We push a1 and m. We push a1 and m, and then we remove this n minus 1. Then we see that we have a 2n at the front. Then we push the two values. Uh, then we remove this, and so on till we get n. Okay, so this is how we searched it, and we can allot. We can store these distance values in an array. We can make an array, and we can store the distance values. Suppose the uh, value of value at the nth index, we can make it 0 because we have started from here, and the distance of n from n is 0. Then the distance of n minus 1 here is 1. So when we strike this off, we assign the values. And 2n, suppose it's here, then its value is also 1 because it's the child of 2n. And similarly for uh, a1, we get value 2 and so on. So, and the first occurrence of m gives us the minimum steps required to make n equal to m. Okay, so one question here is, when we assign the array, what should we make the minimum value of, what should be the value of the array, like the length of the array? Okay, so to solve this, we first need to make an observation that if n was greater than m in the original question, then there was, let me just remove this for now. Yeah. Okay, so if n was greater than m in the question, then the answer would have been simply to keep on decreasing n by 1 until we reached m, right? Because increasing uh, n to 2n and again multiplying it by 2 would just cause, would just increase the, keep on increasing the number, and we won't reach m in the shortest path. Okay, so we have a one observation here, and okay, and to find what should be the maximum value till we have to search, we can see that, if while searching we reach a value k, and suppose k is less than m, because if k were greater than m, then we would simply be decreasing k till we reached m. Suppose k is greater than, suppose k is less than n, then we have two operations, k minus 1, and we make it 2k. Suppose 2k lies to the right of k, then I don't think there's no point again multiplying 2k to reach a greater value, because the shortest path would be to decrease 2k till we reach m. So my point here is, we don't need to search bigger numbers if we don't need to keep multiplying the numbers if they are greater than m. Oh, right. So we don't need to keep multiplying these again by 2, because that won't lead us to a shorter path. Instead, the maximum value we can search is 2m. We can allow ourselves to go till 2m. Uh, right. So this is what I was saying. So the maximum length of the array, the maximum index the array can have is 2m. So now how to implement this? Here I've take yeah. So we've given the input as two integers n and m, and that's all. Here I've taken the input, and I have written my first case if n is less than, sorry, if n is greater than m, then we have to just keep on subtracting 1 from the n till we reach m. So our answer will be n minus n, because that will be the shortest path. And if n is less than equal to m, we just make an array of length 2m plus 1 to store all the values, because that's all the values we need. And that's all the values we can reach uh, while we are on find the shortest path. And we make a queue to store the BFS value, to store the values of the child nodes while we are while doing a breadth first search traversal. And we traverse and we make a condition that while queue is not empty, while a queue has certain values, which we saw earlier. That's how we do a breadth first. That's one way to do a breadth first search. And what we do here is, we just, yeah, suppose there's a certain value val at the start of the queue. We have two options to go to val minus 1 or to go to 2 times val. Now, one thing we have to observe is, if val minus 1 is equal to 0, then there's no point in searching further in this lane, because if we keep on multiplying this, we get 0, and if we subtract 1, then we get numbers which are negative. So, and we don't attain m through this. So if we get this, if we get val minus 1 as 0, if we reach a 0 here, then we stop searching in this branch and we try searching here. And we also saw that 2 into val should be less than equal to 2m, uh, which I've showed before. So this is how we have to write this. First, we take the front value of the queue, then we pop the queue, we remove this value, and we check if, suppose the value is equal to m, then we have reached the first occurrence in the queue, and we have to just print the value into this, print the number of steps it took us to reach here, which was stored in the array, and we have to print it array of val or array of m. We print it and we stop, returned it. And we have to check two conditions. If 2 into val is less than equal to into m, then if we check that if 2 into val has been visited before uh, or not. So if it has not been visited before, then we can change, then we can update its, uh, then we have to enter the minimum distance it took us to reach here. So if array of 2 val is value of value plus 1, array of val plus 1, and we have to push this child of the val node, to push this child inside the queue, right? So push 2 into val, and another condition is if val minus 1 should be greater than equal to 1, which I showed. So again, we check if it has not been visited. So of val minus 1, this in the this child in the, and that's all. I think this should work. Can try this. Suppose, uh, yeah, 4 and 6, we give this input. Yeah, we get 2 as the answer, and suppose we take this 10 and 9, 10 and 1, we get 9. So, yeah, that's it.
Okay. Thank you, Nishant. So, am I audible? Am I audible right now? Okay. So, continue. Now, breadth first search was one way of searching in the graph, and that was useful in finding the distance of how far a vertex is from a source vertex. Now we have another notion of depth first search. Now this is similar. This is also like wandering in a labyrinth with a string and a can of paint. Now what we do in this case is we start with us on a source vertex S, and we take a string and we keep on moving along an edge. Now what we do is we travel along an edge, and if the edge leads us to an already visited vertex, we just come back to where we started. Let's say V was already visited. We come back to U. Now if V is unvisited, we unroll our string, move forward, move to V, paint V visited, set V as our current vertex, and repeat the same thing. So this has the notion of recursion inbuilt into it. No, you're doing the same thing. You go to a vertex, you move around, and if it has been visited, you come back, and if it is not visited, you do the same thing for the next vertex. Now, after a point, you will obviously come to a state where all edges on U lead to visited vertices. Then we keep on going back until we reach a previous vertex V that has been visited, and we do the same thing. So it is going in, and once everything has been explored here, you come back, and then you go inside another uh, area of the graph. And what we do is we continue to backtrack along the path that we have traveled, finding and exploring unexplored edges and repeating the procedure. So, how do you actually implement the algorithm? We will use a similar notion of coloring. We color all vertices white, and we will use a DFS visit function that will visit each and every white vertex. So every vertex that we pass to the DFS visit function, that is a white vertex. Now, each call to the DFS visit routes a new tree of the depth first forest. This will be clearer with the example. And a vertex is white if it is undiscovered. It's the same notion as before. And a vertex is gray if it has been discovered, but you're not sure, or not all of its edges have been discovered yet. So it might be that a portion of that vertex has been discovered and another portion is still pending. So it is still under exploration. And the vertex is black if the exploration is complete. So this is how we would implement the algo. We initially color everything white. We have a timer, time 0. Each vertex in vertex set. If color is white, then we visit that vertex. So we'll come back to it after the example. Now consider this graph. This is U, and now what we do is we notice this edge. We go to V. What after we mark initially V was white, we now color it gray. And after V, next we go to Y. Now we color Y as gray. Next we go to X. Now after we visit X, next we go to X. Now after we visit X, we notice this edge X to V. But V has already been colored gray, so we don't explore V again. We come back to X. These are the timers. 1 at time 1, time 2, time 3, time 4. At time 5, we come back to X and we color it black because there is no more edge left to be explored by X. After this, we come back to Y. All edges of Y have been explored. So at time 6, we color Y black. Now we go back to V. At time 7, we notice that all edges of V, that is only this VY edge, has been explored. So we color it black. Now at time 8, we see from U to X, there is an edge F. Now X has already been colored black, so X is already explored. So we come back to U and we mark it as black because all edges have been explored. Now, if you notice, there is no way you can explore W or Z starting at U. So if you remember, we have this loop. So for each vertex, if color is white, then we visit U. And this for loop definitely traverses all vertices. So now, let's say we reach W next. So this that for loop checks if W is colored white, and that is true. So we color it gray and we begin our exploration. We first check Y, it is colored black, so we come back to W. Next we go to Z, it was white and therefore we color it gray. Now there is an edge from Z to Z. It is also called a self loop. Now because Z has already been colored gray, we just color Z black and we come back to Z and we color it black. Now what we do next is we see that W to Y has already been discovered. We know that W to Z is complete, and so we color W black. And there are no more edges that are white, no more vertices that are white, so our DFS is complete. So when DFS returns, every vertex is assigned a discovery time, the time we entered into it, and a finishing time, the time we exited that we finished exploring it. So the running time is to explore the running time. We notice that each loop in the DFS, each loop in the DFS takes this loop takes O of V time because we are setting colors. This if checking this takes O of 1 time and a total of O of V time. We will analyze DFS visit separately. Now DFS visit is called once for every vertex, and it is in because it is invoked on only white vertices and no vertex is colored white again. So it is called once for every vertex. And if you notice this loop, for loop, for each vertex in adjacency, if color is white, then we visit V. So this for loop takes order of degree time again. So the total time taken inside the loop, excluding this time taken for the DFS visit V, will be order of degree. These are O1 operations, assigning, we mark it as gray, we set the time, we increment the timer, we mark it as black, we set the finish time, we increment the timer. So after we are done with all this, we have spent our order of degree time. So the total time that we take is sum of degree, which is again 2 times the number of edges, so order of edges. So the total cost is of order of V plus C. And now I'll ask Anirudh to continue with the lecture.
Hello, am I audible? Can someone confirm in the chat? Hello? Yeah. So now we'll discuss about single source shortest paths. Uh, so first of what is single source shortest paths? You need to calculate the distances of all vertices from a single vertex. So you can also do this via a BFS. But why do we need a different algorithm for this? Because there's a BFS would only calculate shortest path if the edge weights are 1. Suppose that edge weights are just a second. Yeah. So suppose these edge weights are not only 1 but some 3, 4 or 5, something like this. Then we cannot calculate the shortest paths via BFS. So there's another algorithm called Dijkstra's algorithm to calculate the single source shortest paths. Next. Yeah, so this is just what I said. And one idea could be that we can replace this the edge of length 3. We can replace the edge of length 3 via 3 one length edges. But this would blow up the graph too much, and don't have the memory to store a graph this much large. Yeah, so next, now I will introduce you the what's the Dijkstra's algorithm. In this, suppose now there's a set that we will maintain. It is the vertices. It is a set which contain the vertices for which we have calculated the shortest distances. Uh, at the initialization step, we know that the source vertex has a distance of 0. So only the source vertex would be present in this set. Suppose the source vertex is x, and there's another set which is the non-explode set. Suppose this set is suppose this set is something y, then this is v minus y. Yeah. So now what Dijkstra algorithm says that consider all the edges that cross this frontier, all these edges, and choose the one for which this value is minimum, d of x plus the length of the edge. This value is minimum. Choose that edge. Suppose that edge goes from some vertex x to y. There is some vertex y here. So what we would do is we would set d of y to be equal to this value, and would add y to this set. Y would be removed from this set and would be added to this set. So now uh, I will just dry run on some example. Suppose the graph is something like this. Yeah, so this is the source vertex. Initially we can see that these two edges are the ones that cross the frontier. So out of these two, this one is the minimum. We would choose this edge, this one, and this vertex would also be added to the explode set, and the distance of this vertex would be set to 3. At the next step, what we would do is these two edges, this one and this one, these two edges are the one which cross the frontier. So now we would calculate the value for these two. Here we see that 3 plus 4 is 7 and 0 plus 5 is 5. So the minimum of these two is 5. So we would choose this edge and would add this vertex to the frontier, and would also set the minimum distance of this vertex to 5. And now these two edges are in the are the ones which cross the frontier. 5 plus 1 is 6, 3 plus 4 is 7. So 6 is minimum of these two. So we would add, now we would finally add the last vertex to the explode set and set the distance of this vertex to 6. 5 plus 1 6. So this is what Dijkstra algorithm does. But now, why is this correct? This is just the formal way of writing the Dijkstra algorithm. One more question, one more thing. Here, here it is written that we assume that the length of each edge is greater than equal to 0. We cannot use Dijkstra algorithm if there are negative edge weights. Why is that? Um, because the greedy criteria that we use in Dijkstra, which we'll be proving further, uses the fact that these edge lengths are greater than equal to 0. But now they can be one idea that we can add some constant to every edge weight and some large constant and then apply the Dijkstra algorithm. But why is that wrong? uh, for example, take this graph. This is minus 2, this is 1, this is minus 5. Yeah, so in this case you see, suppose we add 6 to each of these edge weights. So the new edge weights will become 7, 1 and 4. So now we see that this, according to Dijkstra's algorithm, the shortest distance of this vertex would be 4, and when we subtract 6 from it, it would be minus 2. But as you can see that initially it was minus 4, not minus 2. So that is because there could exist some path with more number of edges, but which has a larger, uh, which computes a larger distance. But when we subtract the large constant more number of times, it could uh, finally get to a smaller value. Like in this case, you see that if we go via this path, 7 and 1, it it's, uh, okay, sorry, I thought the whole screen was visible. Just a second. Share screen. Can someone tell from where should I start again? Like, till which part are you clear? Shall I explain the Dijkstra algorithm again? Okay, I'll start with that. Just a second. Is the whole screen visible now? Yeah, so in Dijkstra's algorithm, we have some set in which we have the vertices that are explored and for which we have stored the shortest distance. We have calculated the shortest distance. And there is another set which is the non-explode set. Suppose this set is x and this set is y. Here we have the source vertex s, which is added to the set while initializing, and all the other vertices are in this set. So now what Dijkstra algorithm does is it considers all the edges that cross this frontier, all these edges, and we have to choose the edge for which d of x plus the length of the edge is minimum. X is the set, X is the vertex which is in the explode set, and edges are the ones which are crossing the frontier. So for the edge for which this value is minimum, yeah, mm, for which this value is minimum, we will choose that edge. Suppose that the vertex that connects the edges of small y. So what we would do is we would set d of y to this value, and would add y to this set, and it will obviously remove from this set. So this is what Dijkstra's algorithm is. I would dry run it on some example. Suppose the graph is this. Three, 4, 5, and 1. So initially this is the source vertex. So initially these two edges are the ones which cross the frontier. So out of 3 and 5, 3 is minimum. So we would select this edge and add this vertex to the explode set, and would set the distance of this node to be 3. Now next, these two edges are in the frontier, and we would calculate the greedy value of the Dijkstra. For this edge, this is 7. For this edge, it is 5. So this is the one which is minimum. So we would select this edge and add this node to the explode set. Now, for the last iteration, we have this edge and this edge. For both of these, we calculate the greedy value. This is 6, this is 7. 6 is minimum, so we would choose this edge and set the value, set the shortest distance value of this node to be 6. And now we have explored the whole graph. So this is what Dijkstra algorithm will be run on this graph. So next, I was explaining why we can't add large constants in case of negative edge weights. Suppose the graph is this, and this is 1, -5, and this is suppose -3. Yeah. So consider what will be the shortest distance actually. For this node, it would be -4. For this node, it would be 1, right? But now if we add some constant, suppose we add 6, the new edge weights would be 7, 1, and 3. Now if we run Dijkstra on the newly computed graph, we would find that the shortest distance of this node would be 3. And we would and because it consists of one edge, we would subtract 6 into 1, and that would come out to be -3. But we know that shortest distance is -4 in case of in the original graph. So we can see that there is something wrong with this. Um, to But what is actually wrong? You can see that in this case there is a path with two edges that that computes to distance of 8, but and this path with one edge computes to a distance of 3. But we are subtracting 6 from this from 2 times, and from this only 1 time. So when the last constant is subtracted more number of times, there is always a possibility that this value could be smaller than that, which is the case here. Sometimes it might not, sometimes it might, but that it would not be correct always. So that is why adding large constants would not work. That is clear, Kanishk? Now we'll try to analyze why this algorithm is correct. Yeah. So formal way of writing Dijkstra algorithm is for every graph with non-negative edge lengths, Dijkstra's algorithm correctly computes all shortest path distances. So now, as we see that, as we saw that it adds vertices to the explode set one by one, we would induct on the number of iterations. Initially, only the source vertex is added. So for the base case, we know that source vertex has a distance of 0, so that is correct. So base case is correct. Now the inductive step. Uh, we assume that for all previous iterations, AV equal to LV is the true shortest path in the graph for all vertices V that are in the explode set X. Now in the next iteration, what Dijkstra algorithm does is it picks an edge V star to W star, where V star is in explode set X, W star is in V minus X, and we add W star to X with the constraint that AV star plus LV star W star is minimum among all the edges that cross the frontier. Right? Now if we prove that for W star the true shortest distance is this value only, then a proof would be complete. Right? So what we say is, suppose there exists another path. Suppose there exists another path which has which has the distance computed less than what the Dijkstra algorithm computes. So now that path would cross the frontier at some point. It would suppose till y it is in the explode set. Now it crosses the frontier at this point from y to z, and then with some via some path it might come back to the explode set, might not. Via some path it goes to w star. So the what we say is this path length is smaller than the length computed by Dijkstra. Now we know that for y, according to the induction hypothesis, the shortest distance computed for y is the true shortest distance. Right? Now this edge length is Lyz, and this edge length has to be greater than or equal to 0. This is where the constraint, the assumption that there are no negative weights is useful. Now what we say is, now as we have according to the greedy criteria that we use, we have chosen the edge that connects W star. So it means that there is some vertex. I will draw it. Yeah. So the path was something like this, y, then here it crosses the frontier, then it goes to W star, right? So we know that S is here, Y is here, Z is in here, and W star is also here. So this path, this shortest length path is correct because according to the induction hypothesis for Y, now it crosses the frontier here. So this total path length, what would it be? It would be d of y plus L of YZ, right? And according to the greedy criteria that Dijkstra uses, we chose W star. Why? Because there would exist some vertex, suppose V plus L of V W star is minimum among all edges that cross the frontier. So what does that mean? That this value is smaller than this value, and we know that this path length is greater than equal to 0 using the fact that there are no negative weight edges. So it means there cannot exist any other path which has a smaller distance than the one that Dijkstra chooses. So this is the proof of correctness via induction. Is there any doubt in this, or shall I move forward? Okay, if there's any doubt, just write in the chat. Okay, now, so just a second. Yeah. So now we will discuss another algorithm, that is Kruskal's algorithm. Just a second. Yeah. So Kruskal's algorithm. What? Suppose there is a graph. Suppose there is the intercity roads. These are some intercity roads with some with the weights as distances, 5, 6, 7, 10, 2. Yeah. So now we have to choose. Uh, yeah. So the government wants to make the roads so that wants to spend minimum money and wants all the cities to be connected with each other. We know that a tree is connected. For in a tree, for each pair of nodes, there exists a unique path. So basically, what we want is we need to form a tree that would that would contain the smallest number of edges. But the further condition is it should have the least weight among all the subgraphs of this graph that are trees. We want the one with the least weight. So, Kruskal algorithms helps in finding the minimum spanning tree. Spanning tree means a subgraph which is a tree and it spans across the whole graph. Spans across the whole graph means it contains all the vertices of the graph. So, in this case, uh, we can see that the minimum spanning tree would be this edge, this edge, then this edge, and this edge. No, sorry, not this edge. Only these three edges. Sorry, yeah, only these three edges would form the minimum spanning tree of this graph. So now, what Kruskal algorithm says is first we sort the edges according to their weights. This is the sorted list of the edges. In this case, it would be 2, 5, 6, 7, and 10. And now we iterate in this list and we consider, suppose we consider this edge, and uh, we initialize the tree as this, only the vertices, no edges. And now we need to connect these four nodes with these edges so that we use least, so that sum of the weights is least, is minimum. So we first consider this edge 2. We see that this edge is between this vertex and this vertex. And now, when can we add this edge to this tree? When the nodes that the edge is connected is not already connected in this graph. Now we see that these two nodes are not connected so far, so we will add this edge to this graph like this. Next we consider edge 5. Edge 5 connects this vertex to this vertex. We see that, suppose via some data structure we can check that these two nodes are not connected, so we would add this edge. Now we go to 6. 6 connects these two edges, these two nodes. Now we see that these two are also not connected, so we would add this edge. And now we iterate further till to 7. 7 connects 1 and 4. But as we see that 1 and 4 are already connected in this subgraph, we would not add this edge 7. And same for 10. 4 and 2 are already connected, so we would not add 10 to this graph. So therefore, this is the minimum spanning tree of the shown graph. Now, what are the two operations that we essentially do here? Sorting is the first one, right? The other ones are, we need to check whether two nodes bel- belong are connected or not. We need to check that efficiently. The running time of this algorithm is dependent on how efficiently can we check whether these two nodes, whether some two nodes are in the same set or not. For for uh, to check this, we have a data structure called disjoint set union. Yeah. So disjoint set union, what it does is, we have two operations in that. Suppose these are some sets with only these are the elements, and initially each set has only one element. These are the four sets initially. Now what we can do is, we can combine two sets, uh, and second is, we can check whether some two elements are in the same set or not. These two things we have to do. Suppose like these are, just a second. So 1 2 3 and 4. Now uh, in the previous case, as we saw that when we consider a edge, first we check if those two are not in the same component, are not connected. If they are not, then we add the edge. So now we have to combine these two. We make these two sets as one set, and further same way, like 2 3 we would connect, and we would make this whole three elements in the same set, and again then 4 would be connected, and this whole would be complete one set. Now how we do that efficiently? First of all, for each set we have a leader that represents the set. Initially, when there is only one element in each set, that a single element is the leader of the set. But uh, how do we change the leader when we combine two sets? Suppose a set is of these three elements, 1 2 3, and another set with four elements, 4 5 6 7. We have to combine these two sets. Initially, uh, each element is pointing to the leader like this, and here we have this. These all are pointing to their leader. So now when we combine these two sets, what we do is, we point the leader of the smaller size set to the larger size set. Now 1 would point to 4. Why this? Why is smaller size set leader would point to the larger size set? Now I would make a claim. When we do this, the size of the set at uh, at least doubles. Like in this case, you see this set has 3 elements, and this set has 4 elements. Now when we combine, the combined set has 7 elements, which is more than 3 into 2. We are seeing the size in this set's perspective. So when I claim that whenever we combine sets like this, the size of the finely formed set would at least be double of the size of the smaller set. Now, why is that? Because suppose the smaller size set has size some x and larger one has y. When we combine these two, this would be x plus y, and it is greater than 2 into x because x is greater than y. Yeah. So now each time when we combine, we say that the size of the set at least doubles. So we have n. Suppose we have n elements. Initially, all are single set. All are single sets. So each time we combine, the size at least doubles. So what does that mean? That we can perform the combine operation at max log n times, because when we, for each element, suppose we consider 1, when suppose this element 1. Now when a combine operation is performed to the set which contains the element 1, so the size would double. Then next time when the combine operation is performed, when the when the set contains 1, the size would be doubled. Now it as size will be doubling each time, and we have n elements in total. So for with respect to each element, the combine operation can be performed at max log n times, not more than that. So this is the union operation in terms of disjoint set union. And now next we have to check now next we have to check whether uh, some two elements belong to the same set or not. Are there any doubts so far? No, okay. Yeah. So now we have to check whether some two elements belong to the same set. For that, what we can do is, suppose we have to check for 3 and 6. Till when these two sets were not combined, what we would do is we would check who is the leader of this set. As 3 points to 1, we would get to know that 1 is the leader of set. 1 would only point to 1 because he's the leader. So we get to know that 1 is the leader of 3 set, and for 7 we get to know that 4 is the leader. So as these two are different, we can return that these two belong to the different set, means they are not connected. We need to add this edge. And when 1 is pointing to 4, we check that 3 now. One thing, when we combine, we would also change these pointers. Now 3 would point to 4, 2 would also point to 4, and 1 points to 4. Now, why does this step not increase the time complexity? As I said previously, that combine operation with respect to each element can be performed at max log n times. So it means that the leader of the set for an element would be changed at max log n times. So hence it would not take more than log n time with respect to each element. So now when these two sets are combined, we check for 3 and 7. Now 3 would point to 4, 7 would point to 4. So as both are pointing to 4, we would get to know that we can return that these two are connected and we do not need to add this edge. So this is what essentially disjoint set union is. We would share the resources for this part with you. Are there any doubts so far? If there are any doubts, you can write in the chat. Okay, then we will share the resources for the disjoint set union, and we would, as usual, we share the lecture slides and the problems for the graphs, practice problems for the graphs. And so, I guess that's it. Thank you, everyone. Bye bye.